Hi, this is ET370, Lecture 6C, and in this third part, we're going to go over this Joule thief circuit. It's kind of a nice, fun little automatic boost converter. It actually can be used to take a dead AA battery, or not even dead, 1.5, 8.8 to 1.5 volts, and actually turn on an LED with a forward voltage of approximately 2.5 volts. So it's kind of a fun little device, little circuit. We're going to explore how it works, but before that, we'll do a little review on transformers, so that'll be good. And we'll look at a circuit sim just to see the electrons and the current flowing. And then I actually have a real example that I printed out and to show you. Okay, so let's begin. So the circuit of a Joule thief, and what is joules? Joules is unit of energy, and so this is kind of a play on words. Joules is like crown jewels, but joules is unit of energy to kind of get that last amount of energy out of these dead batteries, right? And so here's what's going on. So we just talked about boost converters, and so you have a kind of a low voltage here, lower than the forward voltage drop of this LED, yet you have this automatic switch that's gonna work in terms of turning this transistor on and off and be able to charge up this L2 here and shoot it through to the LED, right? And so we'll go over how this all works. But before we dive into that, let's just review this transformer. So notice we have inductor 1, inductor 2, but they're mutually connected. So in a transformer-like configuration, we have the two dot conventions, we have our current conventions, and then we also have our polarity here. So let's redraw this transformer. Good. And notice I put N1, N2, L1, L2. Okay. So let's assume it's ideal. So a coupling factor that's nearly 1.999 or something like that. And if we go back to our dot convention, I'll put a link in the description. But if we look at our dot convention rules, you can see that I2 is entering its dot and I1 is leaving. So they have the opposite arrows going to the dot. However, that means from the dot convention, we actually get a positive sign when we write out the transformer equation for the current. So I2 equals positive N1 over N2 I1. And what you can take away from this is that since this is positive, more I1 will induce more I2. So there's this positive feedback that's going to happen. And so you'll have to remember this for the working of the circuit. Okay, what about the voltage? Well, we can see that the positive side here is touching its dot, and same with the positive side of the 2 is touching its dot. And so again, we get a positive. And so V2 equals N2 over N1 V1. Notice the inverse relationship of the turns ratio. Now, if it's 1-to-1, which we actually choose a 1-to-1 ratio here, then the number of turns are equal to each other, and V2 equals V1. So that's another little important fact that we're going to remember and assume for this Joule thief circuit. Okay. So roughly, how does it work? Well, when you start up, this LED is off, okay? And what happens is that transistor essentially turns on, it's in saturation, okay? And when this is in saturation, the current really is not going through the LED at all. The current's just going through here and charging up L2. And eventually what happens is that the transistor opens up. Okay, so it goes into cutoff, and all that energy that was charging up I2 gets dumped into the LED and it turns on. And once that I2 depletes, the cycle repeats, and we get that kind of nice boost converter action where charge up, discharge to the LED, charge up, discharge to the LED. Okay. So let's just look at this more closely. So let's just say this is off and the transistor's in saturation. This is a good review of our NPN kind of stuff here. So if you recall from the first lecture on transistors, the conditions for, oh, sorry, not the first one, the one on the large signal DC analysis, the conditions for saturation are that the current IB, so actually this ends up being IB here, is positive, and beta IB, the gain of the transistor times this, is greater than IC, which is this current here, which is greater than 0, okay? All right, and so let's say that the dead battery, or just the battery itself, is 1.5 volts. Let's say this is a base limiting resistor of 1,000 ohms, and that the beta is 100. All right. And so if we're in saturation, we're going to have this circuit. The only thing I did was I replaced this NPN with the saturation model. So nearly 0.2, just a little speed bump of voltage here, and a 0.7 like the forward voltage of a diode there. Okay. Now notice that by KVL, the voltage of the diode is actually 0.2 volts here. All right, now no current here. And you can think that, oh, well, that's technically forward biased, right? Yeah, but it's less than the forward voltage of the diode. And if the forward voltage of the diode is 2.5 volts, this LED is going to be off. All right, so what's happening? Well, like I said before, the voltage is able to allow current to go through both, right? Both the base and the collector. So this I2 equals IC, and by KCL, I1 equals IB, right? So let's note a few things while we're here and we're looking at this. And this is just good review of the concepts that we've presented. Well, by KVL, what's happening? Minus Vs plus V2 plus 0.2 is 0. So we can see that V2, this voltage here, is actually going to be this 1.5 minus 0.2. So it's going to be a positive 1.3 volts here. Okay, so you got 1.3 volts. Yep, that makes sense. A little KVL loop. This plus this equals that. Okay. If we assume that we created this with a one-to-one transformer, then this voltage is actually the same as that voltage. So this is 1.3. And notice we get a stacking, right? Minus to plus, minus to plus. So the node voltage here is Vs plus V1. Okay, and so we can do a little nodal Ohm's law to figure out what this current is. So that's this node voltage, Vs plus V1 minus 0.7 over R. And what we get is about 2.1 milliamps, right? So the voltage here is actually even higher than normal. Okay, so we get the 2.1 milliamps. That's good. The IB is positive, right? So we're getting base current here. What else? Well, remember that positive feedback symbol, because of the way we have the dots on here, we kind of have it opposite wound, right? And more IB here is going to induce a growing IC, right? So, and more IC is going to induce a growing IB. So they kind of help each other, right? And you can see by KCL, I2 equals IC. And so this current here is going to spool up this inductor, right? L2, okay? And initially, because IC is small, but positive, that's good. That's kind of meeting that IC greater than 0 condition. But beta IB is still bigger initially than IC. However, IC is growing, right? So you're pulling in current, and this guy is, increasing. This current is increasing. Now it keeps increasing until a point. And what's that point? So eventually, this IC grows to a value that IB cannot sustain in that transistor, right? So we get to the point where they're both equal, right? And remember, once this current surpasses what that base current can handle, it now downgrades into forward active, right? It's no longer in a saturation mode, right? You need that base current to keep supporting the IC. In saturation mode, there's plenty of base current to support any IC you want. However, if you're trying to pull too much IC relative to your base current, well, then it's like, okay, well, let's go to forward active. Well, the second it goes to forward active, the voltage here, VCE, is going to start increasing, right? Well, what happens when a VCE starts increasing? Well, you have a little pressure buildup here, and this I2 and IC start to slow down. And if it starts to slow down, do that positive feedback, IB is going to start slowing down because they're kind of in some way connected to each other here. Okay, now what happens to the transistor? Well, once you start losing IB, the transistor is now going to cut off. Okay, and so once it cuts off, you're now in this kind of mode. Well, that's not a bad thing, because now all that stored energy spooling up L2 is now, boom, dumped into the LED, and the LED actually lights up. This is the boost converter action, right? Okay. And once I2 fades down to 0, the cycle repeats back to step 1. Okay. So let's go look at this on the circuit sim and see that behavior. So I'm going to switch over here. Okay, so here's the Joule thief circuit. I have my NPN transistor, I have an LED, I have my 1,000 ohm base limiting resistor, 1.5 volt. Okay, and notice I have my transformer here, and I have it cross-connected. So yes, the Falstad simulator gives me a transformer with the dots on the same side, but look, I can now have this line go here and cross-connect to the bottom before it goes into the secondary transformer now. Okay, so I'm gonna run this. And right now, notice that we're in saturation. You can see we're in saturation, so it's spooling up L2. And then once this goes into cutoff, you can see the LED here lighting up. And you can see I2 is going up. This is I2, which is the same as IC during the saturation condition, right? This is going down, it's dissipating, and then eventually dissipates. And now the saturation mode kicks in. So the NPN now is turned on and L2 again is spooling up. Notice the current for the base is kind of constant around 2 milliamps. All right, good. And then notice the voltage here is 1.3 volts when it's spooling up, right? Right now it's the LEDs on, but wait until it spools up again until we get back into saturation mode. And what you'll see is that that analysis that we did with the KVL takes effect. So once we get there, I'm gonna pause it. So it's spooled down. Okay, let me pause that. So you can see this is 0.2 volts, all right, around, or well, the Falstad model gives us 0.7, but you can see 1.5, and then you can see this about 1.4, 1.3 volt here, right, to satisfy that KVL, okay? Notice these two voltages are the same because I've made this inductor ratio 1, or sorry, this transformer ratio 1. And you can see we get the stacking. 1.5 plus this 1.4 is the node voltage here, okay? And you can see the 2.2 milliamps, right? Now, when I'm running this after it's done spooling up, there's a point at which this current here ends up being 100 times this. So when this gets to about 200 milliamps, the beta times this, that's when it kicks off and goes into cutoff. So wait for it. Boom. So notice when it was 200, that's when it breaks that condition and the transistor cannot handle being in saturation anymore, okay? It downgrades quickly into cutoff and the LED gets the fire in that boost converter kind of situation. So this is the automatic boost converter, and this is a fun little Joule thief circuit. And if you Google it on the internet, you'll see a lot of implementations. All right, so let me stop this and let's go and see a physical implementation. Okay, so we're back here. And if I go to this next slide here, what I have is a circuit diagram where I built a Joule thief. And you can see I have my dead battery, I have a switch, I have my transformer, and I have it connected such that it's cross-connected. My little base limiting resistor NPN LED. Here's the physical layout. Here's my transformer like so. This is my transistor NPN, my switch, with my battery and my LED, and this is the physical implementation, right? So check that out, okay? So here's the LED transistor transformer. You can see the two coils, right? Pretty neat. Okay, so let's take a little LED. So here's an LED, and I have 5 volts, so ground, 5 volts from just using my Arduino. If I touch this to 5 volts, that LED lights up. But if I take a battery here, and I try to power that battery. So I have ground here. Here's the negative. This is what, maybe 1 volt, not even. And I try to touch it here to this, no lighty, right? Okay. And I can even check the voltage. Let me just see. I think this is even less. This is even less than the 1.5. So I take my ground here and I take this. What do I got? 0.2 volts. Wow, it's pretty low. Oh, 1 volt. There we go. We got 1 volt. So not even 1.5 volts. Okay. Yeah, I grabbed this out of my dead battery bag. Okay. So now let's put it in here and let's turn it on. And you can see that this is lighting up. So I have my little LED here and it's lighting up. And I don't know if you can hear it on the microphone, but I can hear this this high pitched frequency, and that's this thing that's ringing and turning on and off to charge up and discharge this inductor, kind of like a PWM, right? So yeah, it's kind of cool. And you can see there's the traces on the back. But yeah, this was created, a few years ago, but just as a fun example for you guys. Well, I hope you enjoyed this lecture, and I'll put links to all the simulations and all that stuff in the description. But yeah, hope you learned something. Have a great day.